Hello everyone, I am Luis Alejandro Bernal Villalobos, and today we're going to solve an exercise together as a preparation for the CRG exam, problem type 2, residence time distribution from the year 2018, month of June. And this guide is part of my master leadership class. So let's jump right into it. So it says residence time distribution in wastewater treatment. It says that some scientists have investigated the residence time distribution in the activated sludge system of the wastewater treatment system in Nancy-Mexeville. Sorry about my pronunciation, in France. The reactor, with some dimensions, has a volume of 3,300 cubic meters and was passed during the experiment with a volume flow of 2,200 cubic meters per hour. Your task is the evaluation of the reactor regarding plug flow and the axial dispersion model. Here we have the residence time, the concentration, and let's read the solution guideline. Point A, sketch the diagram of the breakthrough curve and calculate the average residence time, space-time, of the given system. So I took the freedom to already copy and paste the values that are right here, so it doesn't take too much time. So yes, point A is fairly simple. The breakthrough curve is just to plot time against concentration values. And as we expected, we have something that resembles a normal function, and the average residence time is around 70. But yes, that's just a rough calculation. We can make this much more accurate by taking the mean value uh, of the time, of the residence time, I mean. So there you have it. Here is the average residence time. Let's not forget the units. That is always important in minutes. And yes, that it's point A, 3 points right there. One disclaimer, my Excel, as you can see, is in Spanish, so you're going to need to find the functions and the bottoms in English or your language, your mother language, but I don't think that it's such a problem. Yes, these equations, these two equations, I took them right from this guide, and the other two are part from Mr. Schutz's notes from class. So let's continue with point B. It says determine the Bodenstein number BO of the wastewater treatment system by linear regression. The axial dispersion model has the following analytical solution. In this equation, C star is the relative concentration, which can be calculated by C times F equal the signal C from lithium concentration measurement times unknown factor F. The linearization leads to the form. So this equation is just this same equation, but manipulated with natural logarithms. Draw a diagram, Lagrange logarithm with 2 times, well, these values versus x to determine the Bodenstein number BO in the adsorption process from the slope. Diagram in Excel results in less points than on paper. Okay, so this point is pretty straightforward. It's a linear regression. So let's remember the equation from a line. It's y-axis, it's equal to the slope times x-axis plus the intercept. So we want to resemble this equation to this equation. So as we can see here, the y-axis is the left-hand side of the equation. The x-axis is expressed right here by this expression, and the intercept is this natural logarithm. So before we start, we need to calculate, as we can see in this equation has omega several times. So we need to calculate omega, and omega is just the division of time and the average tau that we calculated in the last point. So let's copy and paste all the data that we need. And let's start by calculating omega. I'm going to copy and paste this equation because it's going to be useful for this point. Okay, so let's calculate omega, that it's time divided tau. So what would be the time divided the average residence time that we calculated from the previous point? Don't forget to lock cells that are not going to be moved. So we have omega, nice. And let's go back to this equation. Let's calculate the x-axis. Here they tell us what is the x-axis. So let's do that. That would be minus 1 times 1 minus omega squared. Wait a second. What is the squared? Okay, I found it. Sorry for that. Squared, yes, divided by 4 divided by omega. So we have the x-axis. Okay, and let's continue with the y-axis. As we can see, the y-axis is the left-hand side of the equation, this part. So let's calculate that. The y-axis would be the natural logarithm of what? It would be the natural logarithm of 2 times the square root of pi times omega times the concentration. Okay, that would be the y-axis. Let's check that everything is correct. It appears so. So right now we are ready to make to plot our linear regression. Fairly simple. We just take the x and y values and we plot them in a dispersion diagram. Okay, so here we have our diagram. To extract the data that we need, let's add a tendency line. And we want to present the equation and the r-squared coefficient just to see how good our regression is. Okay, so here we have our data. We have our our slope, our intercept, and our squared value. We can see that the r-squared value, it's big, but it's not big enough. We can see that many points are not over this predicted line, so the linear regression is not that accurate. But okay, let's extract the data that we need from this graph right here. We can do it with yes, let's just copy and paste it, like just copy from here. So the slope we can see from here, it is 20.843. Okay, that is all what we need from this diagram. And we can see from the linear regression that the slope is the Bodenstein number. So the Bodenstein number would be simply the slope, and that would be point B. This would be the answer, 20.843. So there you have it, 10 points right there. So let's continue with point C. Improve your calculation by variation of the mean residence time. Finally, draw a diagram, lithium concentration versus time, to compare your model with the measured data. So, okay, this next point is fairly similar to this one. So we need to improve our calculation by varying the average residence time. So let's start with this value that we calculated from point 1. This is going to be changed, but I'm going to explain that in a moment. Let's take the data that we need from this, from here. Okay, and okay, so what are we going to do? So to solve this type of problem, we need several data from this linear regression. We need the slope. So let's calculate first the slope. We use the Excel predetermined function to obtain the slope of a function. we can also obtain the intercept using the predetermined function of Excel intersection with the x's, and we can obtain the R-squared coefficient. These are all values that you can see from the previous diagram. R-squared coefficient. But yes, we need them locked in a cell because they are going to change in our optimization problem. So let's just hang on for a moment. I'm going to explain that in a moment. Let's plot once again this data so we can see how our solution affects the diagram. Sorry, it's not copy and paste. It's just selection. So let's insert a dispersion diagram just as before, and it's exactly the same data, exactly the same values. Let's add a tendency line, lineal one. We present the equation and the R-squared coefficient that, as you can see, are the same ones from here. So let's read once again the problems. Improve your calculation by variation of the mean residence time. Okay, so it says that we need to change the mean residence time. This one is going to be changed in this point somehow. So let's not forget that omega depends from this average residence time, t over tau. Okay. So what are we going to maximize? So what we are going to maximize in this optimization problem is the squared coefficient. Let's remember that this coefficient tells us how good our regression is. So if it's 1, the linear regression is perfect, and if it's 0, it's the worst linear regression ever. So what we're going to do is to maximize the R-squared coefficient to see how that affects the Bodenstein number. So to do that, we go to data. Sometimes the solver tool is not activated in Excel. If it's not in your Excel, you can watch a video on YouTube on how to activate it. It's fairly simple, but I'm not going to do that here. So we're going, as I said, we're going to maximize the R-squared coefficient to make it the model as linear as possible. And what are we going to change? As the problem says, we're going to variate the average residence time. Average residence times. Okay, and now we are going to solve the problem. Wait a second, I made a mistake here. It's just this value. Okay, and as you can see, it says here that it converged to a solution, so all the restrictions are fulfilled. We put accept. As we can see, the R-squared coefficient is almost 1, and let's see how this affects the data that are of our concern. In this case, the Bodenstein number. So as we can remember, the Bodenstein number is just the slope from this linear regression. So the Bodenstein number would be just equal to the slope, and this would be the improved Bodenstein number. And if we compared this Bodenstein number to the previous one, we can see that they are fairly different. This is 29.5 and this is 20.8. So there is a significant change in this Bodenstein number, and this can be seen reflected in the R-squared coefficient. If we want to see like more evidence, we can see in this diagram that these points fits very nicely in this linear regression. Not like as here, that the points are really spread forward. Here they are really close to the line, and the values that are here are the same ones that are from here. But in this problem, I needed to have this value or data locked in some cells, so they could be changed during the optimization of the solver. Okay, so that would be the optimization of point C. Let's continue reading. Improve your calculation by variation of the mean residence time. Finally, draw a diagram lithium concentration versus time to compare your model with the measured data. Okay, so now we want to compare our model that we just obtained with the measured data. For that, let's copy and paste this equation that we are going to use for the axial dispersion model equation. So for that, now what we'd like to obtain is this concentration, but with our new Bodenstein number. We already have the Bodenstein number, the pi, the omega, but we need this f value. So now the question is how to obtain this f factor. If we see also in this previous equation, just let me copy and paste it once again. Okay, so we can observe here that in the linear regression, the intercept is equal to this natural logarithm of the Bodenstein number, the square root of the Bodenstein number, divided this f factor. So if we have the intercept and the Bodenstein number, we can solve for this f factor. Already done this. You can check this at home, but solving intercept equal natural logarithm of this expression would be square root of the Bodenstein number divided, divided the exponential function of the intercept. Okay, that would be our f factor. Just give me a second. I want to check that everything is correct. Yes, everything looks nice. Okay, so now we have extracted all the information that we could from our linear regression. And now what we're going to do is to compare our linear regression with the experimental data. Let's remember, this is the experimental data. And as I said before, we would like to calculate this concentration from the axial dispersion model. So for that, we need to first calculate what is here in the right-hand side of this equation. And just put it a little bit smaller. No, let's put it bigger because I cannot see it. And I put it at the end. So yes, it would be the right-hand side of this equation. It would be equal 0.5 times the square root of the new Bodenstein number, the improved one, divided pi divided omega. We have omega right here. Okay, that would be the square root. And that would be times the exponential function of this expression. But let's not forget that this expression is the x-axis that we have already calculated before, so that saves us some time, times the Bodenstein number once again, locked. Okay, that would be the right-hand side of this equation. And finally, we can calculate we can calculate the concentration, but this time this would be from the axial dispersion model. And what is that? It would be this right-hand side divided by this f coefficient that we calculated before. Right-hand side divided this f coefficient. And now we have our concentration that is predicted by the axial dispersion model. So everything looks fine. Now we are ready to observe all this data in a diagram. So we're going to select the data. This would be the experiment. We are going to first plot the experimental one. The x-axis would be the residence time. The y-axis would be the concentration given by the problem by those scientists. And let's add our axial dispersion model, taking the same residence time, but now the predicted concentration. Okay, so that's all for this diagram. Just let me put it a little bit different so it's nice to observe, to digest. Let's add a legend. We're going to put this legend below the diagram. We're going to change the type of diagram for the dispersion model. Experimental values should always be points, dispersion types of graph, and mathematical models should be curves. Okay, so this would be the last part of this point. We can see that our optimized model fits really good the dispersion model. It predicts, as we can see here, 0.99, that would be 99% of the times, the experimental data. So yes, that would be everything for this point. The point D, discuss the results. How can you explain the difference between the calculated spacetimes and the time found value of optimization? Well, that argumentation should be taken care by your own, but it's pretty much just a summary from what I've said so far. And yes, that would be the all for this point. I would definitely recommend to do this point in your exam because, as you can see, it's not that long. It's pretty straightforward, and you can see at the end if your regress model fits nicely to the experimental data. So thanks very much for listening, for watching. If you found this video useful, please fill down the survey down below. If you have any comments, questions, or suggestions, you can also write them in the comment section of this video. And yeah, I wish you success on your final exams.